Does world need energy? The world will need significantly increased energy supply in the future, especially cleanly generated electricity. Electricity demand is increasing about twice as fast as overall energy use and is likely to rise by more than half to 2040. Clean, reliable, affordable, balanced and sustainable energy. Growth in the world's population and economy, coupled with rapid urbanization, will result in a substantial increase in energy demand over the coming years. In fact all the responsible authorities seeks clean, reliable, affordable, balanced and sustainable energy on their energy plans respectively. Nuclear energy. Nuclear power provides over 10% of the world's electricity, and 18% of electricity in OECD countries. Almost all reports on future energy supply from major organizations suggest an increasing role for nuclear power as an environmentally benign way of producing reliable electricity on a large scale. Clean, reliable, green, low-cost source. Furthermore, it is especially suitable for meeting large-scale, continuous electricity demand where reliability and predictability are vital, hence ideally matched to increasing urbanization worldwide. Climate change and global warming. Due to the effects of global warming and climate change, decision makers, media, and the public to realize that the use of fossil fuels must be reduced and replaced by low-emission sources of energy, such as nuclear power, the only readily available large-scale alternative to fossil fuels for production of a continuous, reliable supply of electricity. Furthermore, a major topic on many political agendas is security of supply, as countries realize how vulnerable they are to interrupted deliveries of oil and gas. The abundance of naturally occurring uranium makes nuclear power attractive from an energy security standpoint. Learning object. Learning content. Achieving competency. Develop strategies. Knowledgeable with the subject. Number 1 Nuclear reactions. Number 2 Nuclear fuel cycle. Number 3 Nuclear reactor types.
Hello everyone, I am Malinda Ranavira from Sri Lanka Atomic Energy Board. I am going to explain the nuclear power technology under the program on electricity generation using nuclear power in Sri Lankan context. At present, 445 commercial scale nuclear power plants are operating worldwide. The world will need significantly increased energy supply in the future, especially cleanly generated electricity. Electricity demand is increasing about twice as fast as overall energy use and is likely to rise by more than half to 2040. Growth in the world's population and economy, coupled with rapid urbanization, will result in a substantial increase in energy demand over the coming years. In fact that all the responsible authorities seeks clean, reliable, affordable, balanced and sustainable energy on their energy plan respectively. Nuclear power provides over 10% of the world electricity and 18% of electricity in most developed countries such as OECD countries. Almost all reports on the future energy supply from major organizations suggest an increasing role for nuclear power as an environmentally benign way of producing reliable electricity on a large scale. Furthermore, it is specially suitable for meeting large-scale continuous electricity demand where reliability and predictability are vital, hence ideally matched to increasing urbanization worldwide. So today, first of all, I am going to explain on how nuclear fission and nuclear fusion reaction are happen. When happening nuclear fission reaction, approximately 202 mega electron volt energy is released. In addition, most of the commercial nuclear power reactors are nuclear fission based reactors. In nuclear fission, nucleus of an atom breaks up into two lighter nuclei. The process may take place spontaneously, in some cases so may be induced by the excitation of the nucleus with a variety of particles. As an example, neutrons, protons, deuterons or alpha particles, or with electromagnetic radiation in the form of gamma rays. In the fission process, a large quantity of energy is released. Radioactive products are formed and several neutrons are emitted. These neutrons can induce fission in a nearby nucleus of fissionable material and release more neutrons that can repeat the sequence, causing a chain reaction in which a large number of nuclei undergo fission and an enormous amount of energy is released. If controlled in a nuclear reactor, such a chain reaction can provide power for welfare of the mankind. Next, I am going to explain on nuclear fusion reaction. Two or more atomic nuclei collide at a very high speed and join to form a new type of atomic nucleus. When nuclear fusion reaction happen, deuterium with tritium creating helium-4, freeing a neutron and releasing 17.6 mega electron volt of energy as per the Einstein equation. Now we will discuss about nuclear fuel cycle. The nuclear fuel cycle is the series of industrial processes which involve the production of electricity from uranium in nuclear power reactors. Uranium is a relatively common element that is found throughout the world. It is mined in a number of countries and must be processed before it can be used as fuel for a nuclear reactor. Fuel removed from a reactor after it has reached the end of its useful life can be reprocessed so that most is recycled for new fuel. The various activities associated with the production of electricity from nuclear reactions are referred to collectively as the nuclear fuel cycle. The nuclear fuel cycle starts with the mining of uranium and ends with the disposal of nuclear waste. With the reprocessing of used fuel as an option for nuclear energy, the stages from a true cycle. To prepare uranium for use in a nuclear reactor, it undergoes the steps of mining and milling, conversion, enrichment and fuel fabrication. These steps make up the front end of the nuclear fuel cycle. After uranium has spent about 3 years in a reactor to produce electricity, the used fuel may undergo a further series of steps including temporary storage, reprocessing and recycling before waste are dispose. Collectively, these steps are known as the back end of the fuel cycle. Therefore, nuclear fuel cycle can be divided into two parts such as nuclear fuel cycle front end, it means uranium mining, uranium milling, uranium conversion, enrichment and finally fuel fabrication. And under the nuclear fuel cycle back end, it goes to waste conditioning, waste management, waste storage and radioactive waste monitoring can be categorized. Nuclear waste can be conditioned as per the low level, intermediate level and high level waste. In addition, nuclear fuel can be recycled as uranium mixed oxide. Also, it can be called as MOX fuel. In addition, nuclear waste transportation and waste storages proceed as per the International Atomic Energy Agency's standards worldwide. Enrichment levels are different to each other for the nuclear power reactor or research reactor or nuclear weapon. Also, what kind of enrichment techniques are available in the current world? Enrichment level in different conditions can be categorized as for a nuclear power reactor, enrichment level is 4 to 5%. For the research reactor, enrichment level is 20%. For the nuclear weapon, enrichment level goes to 90%. Main types of nuclear fuel enrichment techniques are centrifuge technique, gaseous diffusion technique and laser technique. Laser technique is developed by the General Electric Hitachi joint venture based on USA. Main type of nuclear waste management technique is vitrified system. During the vitrified system, the process waste convert into the glasses. Next, we are going to discuss the various type of nuclear power reactors which are available in the current world. Those nuclear power reactors are mainly can be categorized as pressurized water reactor, PWR, a kind of a light water reactor, boiling water reactor, BWR, it's also kind of a light water reactor. Then pressurized heavy water reactor, PHWR, it can be called as CANDU reactor, and graphite moderated gas cooled reactors, GCR, it can be called as Magnox reactors, and also fast breeder reactor, FBR. Light water reactors are categorized as pressurized water reactor, PWR, and boiling water reactor, BWR. Enriched uranium used as the nuclear fuel and demineralized water, light water, used as a coolant and thermal nutrient, used as the moderator in this kind of reactor. BWR, boiling water reactor, operates as direct heat cycle and 22% of current nuclear reactors are categorized into this BWR category. Pressurized heavy water reactor, PWR, operate as indirect heat cycle and 66% of current nuclear reactors are categorized into this PWR category. The light water reactor, LWR, is a type of thermal neutron reactor that uses normal water as opposed to heavy water, as both its coolant and neutron moderator. Furthermore, a solid form of fissile elements is used as fuel. Thermal neutron reactors are the most common type of nuclear reactor, and light water reactors are the most common type of thermal neutron reactor. Next, we are going to discuss about the mechanism of the pressurized heavy water reactor, PHWR. This reactor, also named as CANDU, and it abbreviated as Canada Deuterium Uranium. This reactor, natural uranium used as the fuel, and heavy water, deuterium oxide, used as a coolant, and thermal neutron used as the moderator. Special features of this reactor type is on-load refueling ability. It means when reactor is running, fuel can be loading into the reactor. The heavy water coolant is kept under pressure, allowing it to be heated to higher temperatures without boiling, much as in a pressurized water reactor. While heavy water is significantly more expensive than ordinarily light water, it creates greatly enhanced neutron economy, allowing the reactor to operate without fuel enrichment facilities. It means offsetting the additional expense of the heavy water and enhancing the ability of the reactor to make use of alternate fuel cycles. 11% of current nuclear reactors are categorized into this Canadian deuterium reactor. It means CANDU reactor category. Graphite moderated gas cooled reactor, GCR. GCR are early types of nuclear power reactor which was operating during 1950s to 1980s in United Kingdom and France. A gas cooled reactor, GCR, is a nuclear reactor that uses graphite as a neutron moderator and carbon dioxide as coolant. Although there are many other types of reactor cooled by gas, the terms GCR and to a lesser extent gas cooled reactor are particularly used to refer to this type of reactor. The GCR was able to use natural uranium as fuel, enabling the countries develop them to fabricate their own fuel without relying on other countries. For supplies of enriched uranium, which was at the time of their development in the 1950s only available from the United States or the Soviet Union. There were two main types of generation, one graphite moderated gas cooled reactors. The Magnox reactors are developed by the United Kingdom. The UNGG reactors developed by the France. UNGG means uranium natural graphite gas. Those two are developed by as a generation 1 gas cooled reactor at that time. The main difference between these two types is in the fuel cladding material. Both types were mainly constructed in their countries of origin with a few export sales. Two Magnox plants to Italy and Japan and one UNGG sent to Spain at that time. Both types use fuel cladding materials that were unsuitable for medium-term storage under water, making reprocessing an essential part of the nuclear fuel cycle. Both types were, in their countries of origin, also designed and used to produce weapons-grade plutonium, but at the cost of major interruption to their use for power generation, despite the provision of online refueling. This kind of reactant, due to some safety issues, currently most of gas-cooled reactors are decommissioned. Last one is we are going to discuss as the fast breeder reactor. Fast neutron used to vapor over the mechanism inside the reactor. Those kind of reactors are still in the research and development level and still not commercialized by any country. A fast breeder reactor generates more fissile material than it consumes breeder reactors. Achieve this because their neutron economy is high enough to create more fissile fuel than they use by irradiation of a fertile material such as uranium-238 or thorium-232 that is loaded into the reactor along with fissile fuel. Breeders were at first found attractive because they made more complete use of uranium fuel than light water reactors. But interest declined after the 1960s as more uranium reserves were found and new methods of uranium enrichment reduced fuel costs.